Okay, in this homework problem, we're going to continue on using our plate with a hole mesh, and now we're going to investigate numerical convergence. If you remember, at the end of last time, I said I wanted you to use I think it was a 4mm size mesh, and then mesh seed, and then I wanted you to do one other mesh seed, and then I wanted you to see what the results were. Now, what you should probably experience is that you get different stress concentration factor results for different mesh seeds. So we're going to investigate that a little bit further today, a little bit more formally. We're going to take a look at numerical convergence. After that, and this will probably be in the second part, we're going to create an optimized mesh. We're going to probably use hypermesh to do that. And we're also going to look at using second order elements to come up with our stress concentration factor. So if you remember last time, we said that our stress concentration factor from that chart for our geometry looked like it was going to be about 2.5. So let's see what we get when we use a couple different mesh seeds. So I've already called up ABAQUS. Let me bring it over here. And just to remind ourselves what we started with last time, let's go ahead and redo it. So I'm going to go in here to the mesh panel. This is my CAE file from before. I'm going to set a seed size of 4. I'm going to hit OK. I'm going to delete the previous mesh. I'm going to mesh it. And I'm just going to go ahead and overwrite my old job 1. You may want to save the results if you want to take some pictures later. So you may want to call these different job names. But let's go ahead and submit this. It says files exist, so let's go ahead and overwrite them. And it shouldn't take very long here, particularly for this mesh size. And it's running, and it's completed. Now, for this, you really need to use the teaching edition of ABAQUS that we talked about. If you don't use the teaching edition, if you try to use the student edition, you're going to run out of nodes, I'm afraid. So it's completed. I'm going to right click on that, and I'm going to select my results. And as we did before, we're going to select the S22 results. And because of the way I set up this mesh, we talked about this in class as well, the load that's applied on the top edge gives me a nominal stress of 1 megapascal down on the bottom. So this number right here represents the highest stress in my mesh at the most highly stressed node, and it happens to be 2.117. Now I have an Excel spreadsheet opened up. I want to put that number in there, 2.117, and I also want to find out how many elements are in my mesh. So in the results screen, I'm going to go to Tools, Query, and Mesh, and down at the bottom it's going to show me how many elements I have in this mesh. And I want to write that down as well. So here's my highlighter. It says I have 715 elements. So I'm going to go 715 in my X column. We're going to make a chart, and my stress concentration factor of 2.117 in the next column for my Y values. Okay. Now we can animate this. We can look at the deformation. You'll see similar to what we had last time. But let's go ahead and go back to the model. We'll go into the mesh panel, and we're going to change our mesh seed. Let's go a little bit coarser. Let's try an 8mm size, and we'll hit OK. We'll delete that mesh and then remesh it. And now I'm going to submit this job. Alright, so it shouldn't take too long. It will depend on your computer and everything. But now it's completed, so we're going to look at the results. Again, we're going to switch over to S22. And here it is. We have a value of 1.828. We're going to query the mesh. And now we only have 176 elements, so we're going to record that value as well. So our stress concentration value that we calculated has gone down. This 8mm seed mesh really doesn't look like a very good mesh to me. It doesn't capture the curvature around the hole very well. So it's probably not a good answer, and it's less than what we had with seed size of 4, and it's nowhere near what we think should be the right answer of about 2.5. So instead of making this coarser, let's make the thing smaller. So let's repeat this process with the seed size of 2. So we have 8, 4, let's just cut it in half and do 2. We'll go back to mesh, go back to the model, and then go back to the mesh. Remesh it and resubmit it. Now you start to see now there's a lot more elements. Just by increasing that size, decreasing that size from 4 to 2, we have a lot more elements in there. Let's go ahead and submit this. And we'll do the same thing for 1mm and 0.5 millimeters. Now one of the things that you might notice is that it's going to take a few more seconds each time we submit this job for this job to complete. Okay. Again, selecting S22. Looks like we have 2.414. Put that in my spreadsheet, and if I query the mesh, I have 2,858 elements. All right, let's cut it in half again. We have it seeded, we're going to mesh it. Okay, a whole lot of elements now. And we'll submit it again. I'm just going to overwrite those files. We'll let it run. And now it's complete. So it's still going pretty fast. Look at the S22 results. And you see these stress contours, they're a little smoother now. They're fairly smooth. Okay, with the S22 we have a stress concentration factor of 2.516. Let's query the mesh, and we're going to write down the number 11,729. Oh, that's the number of nodes. So we're going to write down 11,718. Those are the number of elements. Let's see if we can do one more. These are starting to get to be pretty tiny elements. And let's do something else. On this mesh, let's zoom in on the bottom. And with these nodes, we can have a variation of the stress. With these elements, we can have a variation of stress within the element. So from one side to the other, it can change a little bit. If we were to look at the theoretical solution for the stress field as it drops off with this radial distance for a plate with a hole, we'll find that it's fairly steep right next to the hole. The gradient of that stress distribution is fairly high. So these stresses change fairly quickly in the beginning, and then they kind of don't change as much over here. That's what that contour is telling us. We could make an XY plot of the stress distribution along this line if we'd like. We'll probably try that a little bit later. All right, so let's go back and reseed it. Back to the model, mesh, and we did 1, so let's do half. And this might even take a minute or two just to mesh this, because these elements are going to be pretty tiny. Now our stress concentration factor chart said that we should get pretty close to 2.5. Now that stress concentration factor chart was derived from some analytical solutions done quite a few years back, well before computers were around. Some of the stress concentration factor charts that you might run across may have been determined experimentally as well, with something called photoelasticity. But here we're seeing what happens when we use this finite element analysis. All right, now look at that mesh. That is got a lot of elements. It's pretty tiny. I'm hoping this will run for us on our teaching edition. But take a look at that. Extremely fine mesh size that we have here. Now let's go to submit it. And it'll probably run pretty quick, but I'm sure it'll take just a few more moments than it did the last time. In the output files, you can find the CPU seconds that it takes to run a job. You may be interested in that for very large jobs. In the end, everything costs some money. So the longer a job takes to run, the more electricity you're using, and just the more time it takes to get your result. Okay, so it's done now, and we're going to go to S22, and there it is. It looks very dense in here. That's kind of a weird auto-meshing algorithm. You can kind of see that it has kind of a spot that it likes, and then it builds the mesh around it. There's some very sophisticated auto-meshing algorithms. All right, so this one says 2.612. And let's go and query the mesh and see how many elements we have now. 47,890. There's so many elements in there that stress contour doesn't look very good. So let's go and go to Options, Common, and instead of having exterior edges, let's just do feature edges of the mesh. And that has this nice looking type of contour. Okay, so that looks this looks real nice. Let's animate this and see what that looks like. Okay. So the behavior looks good. This hole is getting stretched out. Now this is an exaggerated deformation. It's quite large. We're not applying a very big stress on this, so the scale factor for the deformation is 21,414. That's a huge thing. But it's always handy to animate this with an exaggerated deformation, so you can see if anything unusual is happening in your mesh. Let's go to the last frame. I want to point out something else. So right here, the stresses change a whole lot. So we go from this red all the way to the green in the distance of a few millimeters. So it's 2.612 all the way down to maybe about 1.5 megapascals of stress, all in the span of a few millimeters. That's a pretty steep gradient. But if you look out here in the rest of this mesh, it's all pretty much constant. It's somewhere around, well, 0.8. We applied a 0.8 axial stress, so that it makes sense that out here it should be pretty much 0.8. And it's kind of interesting that the contour goes over into here. Right? And right around here, it should be pretty close to zero stress according to the theory. And it looks like it says maybe at this point it's around 0.168. We could probe that value and find out. Let's go ahead and do that. Probe values. Try to get the node right down there on the end. I think I might have to zoom in on that. And I had elements selected, so I need to change this to nodes. And 0.011, so it's a pretty small value, and that's good. Now, since this mesh way out here doesn't really do anything for us, we don't really need all those elements way out here. We really just need all those elements where we have a steep stress gradient. In some problems, you don't know exactly where the stress gradient is going to be, but in a lot of problems you do. Anytime you have any kind of stress concentration, you're going to get a steep stress gradient. It could be a crack, could be a hole, could be some sort of notch. Those sort of things cause steep stress gradients. Near that stress gradient, you want to locate the densest part of your mesh. And away from that, the stresses don't change very much, so you can get away with larger elements. In order to pick up the stress gradient, you need a lot of elements in that spot. Well, I put together this on an Excel sheet, so let's bring this over here, and we'll take a look at the convergence plot. And this is just a real quick and dirty Excel plot, but here are the numbers that we came up with. And look at this as the stress concentration factor goes with the number of elements. We're increasing very steeply initially, and then after a while we don't get a lot more change for a huge increase in the number of elements that we've got. A plot of this stress value versus your number of elements is what's called a convergence plot. Now, ideally, when you construct a convergence plot, you want to have your elements split in the middle each time. Let me show you what I mean by that. Let's go back to my sketch pad. So if I have an element that looks like this, I would want to split that right in the middle and turn that into 4 elements. And if I wanted to do an additional convergence plot, I would take those 4 elements and I would split each one of those into 4 more elements and repeat that process. ABAQUS doesn't appear to me to be set up very well to do this type of convergence analysis, so that's why we changed the mesh seed size. We can still get a convergence plot like we did. It's just that sometimes if you use kind of intermediate mesh seeds and it doesn't quite split them in half, you may get maybe a non-monotonic convergence plot, or it doesn't look exactly like the plot that I showed. In general, your convergence plots, like for ours, our stress concentration factor, as the number of elements increase, you start to see this level out. Now sometimes you can have non-monotonic behavior. It can go up, it can overshoot the stress concentration value that we thought it should be, and as we saw, we got 2.6 and we thought it ought to be 2.5 from the chart. Sometimes when you use way too many elements, a lot of elements, you can over stiffen your structure. That's kind of an artificial stiffening. Now let's go back and look at that Excel sheet, and let's calculate the percent change from this step to this step. So I'm going to take this one minus this one, and I'm going to divide it by that 2.6 value. And I guess I need to multiply it by 100 to get a percentage. So look, between the 11,700 elements and the 47,000 elements, I had a change in value of 3.7%. To me, that indicates I have a pretty well converged value. Now, which finite element mesh should you use? Well, I would use either the one that gave me 2.516, or you could use the 2.612. Well, in fact, we're going to make an optimized mesh in a little bit in part 2 of this homework set, where we're going to probably be in between those values. Now, any numerical analysis is going to have some sort of error built into it. Can you live with 3.6, 3.7% error? Well, if all of your other unknown values are greater than 3.6, maybe your yield stress or maybe even your modulus of elasticity may not have that tight of a tolerance on it, then yeah, the 3.7% is a good value that we can use. Now, if you have a lot tighter tolerances, if you're trying to get something accurate to within 1%, well, it's tough to do in engineering. You would have to look at your problem very carefully, make sure that it was physically meaningful in engineering to get a 1% error on something. But it's possible. So we could use the 47,000 element mesh if it was justified. But even in that case, I would use an optimized mesh. There's way too many elements in there. Now here's another thing to be careful about. The mesh that we're going to optimize is only going to be optimized for loading in the vertical direction. If we come back later and we put another load, maybe in the horizontal direction, on our plate with a hole, then we may have to go back and check our convergence results for our particular finite element mesh. Now, for part of your homework, I want you to go ahead and show this convergence plot, but please clean this up a little bit. So put titles, put axes labels, maybe put the tick marks on the inside. I won't do all of that here, but there are ways to make nice looking plots in Excel. Don't just go with the default. Alright, so what we'll do next then is we're going to use hypermesh, and we're going to create an optimized mesh, and then we're going to see what happens when we use something called second order elements. Alright, so let me stop this video here and I'll fire up part B.